Good day, we are Group 9 and our presentation is on the analysis and design of an inductive based temperature sensor. Our group members are Aidan Pinard, Giovanni Alexander, Jared Mohan Singh and Samantha Dernerain. Introduction. Temperature sensing has a range of applications in private or large scale which would dictate the operating parameters and design considerations. This presentation focuses on an inductive temperature sensor design, which could be integrated into industrial applications for temperatures of fluids up to 250 degrees Celsius. Temperature sensors are important in safety applications, detecting overheating, and serving to alert personnel during hazardous situations, as well as in quality control and process optimization. The importance of temperature control and monitoring can be seen in safety standards such as the ANSI 358.1 2014 standard. Inductive measurement allows for a robust sensing technique that is effective in both time and frequency domains. Temperature sensors can be designed using inductors. One such example is an induction hob designed for domestic use. The focus of this research is to design an inductive temperature sensor by investigating the effect of the material properties of a ferromagnetic core and the inductance of a solenoid due to changes in temperature. The relationship between the geometry and permeability for a solenoid sensor will be investigated. The response of the sensor will be tested by varying the temperature of an object being measured. This data will be used to calibrate the sensor by relating a change in inductance with known temperature values. The choice of materials with respect to the overall cost will also be considered. Applications. The inductive components are commonly used to communicate with a radio frequency identification tag through inductive coupling. The implementation alongside the selective geometry would have varying effects on the inductive sensor in terms of sensitivity and the viable applications. This includes the inductance of variable magnetic components and inductive sensors designed for high-temperature applications. The electrical properties of an inductor are affected by temperature. For example, the change in inductance can be related to temperature by the impedance of the system. Equation 1 represents this. LC resonant circuits with a temperature-sensitive capacitor can be used to relate temperature and resonant frequency. This is represented by equation 2. The temperature affects the capacitance and the resonant frequency, which then affects the inductance of the sensing coil. Another inductor application is in magnetic materials such as ferrite core variable inductors. These inductors make use of the direct proportionality relationship between AC magnetomotive force and the temperature of the magnetic core. In this case, the inductance is seen to vary slightly with the corresponding core temperatures and control current typically decreasing for higher core temperatures. Another inductance sensor application can be seen in the microstrip line geometry. In this case, a superconducting wire is used to tune the resonant frequency of the microstrip line by varying its inductance through changes in temperature or current. This relationship is represented graphically as shown in Figure 1. System overview. The sensor is being designed as a part of a system to measure temperature with a given environment. The system consists of two main components, the circuitry to measure the current flowing through the sensor and the design sensor. The sensor is designed in such a way that the sensor probe is in direct contact with the sensing environment. The impedance of the system is expressed in terms of temperature. The temperature can be measured by the current flowing through the circuit. Measurement principle. An inductive sensor measures a given property by finding the relation of that property to its inductance. The chosen inductive coil design is a solenoid coil with a ferromagnetic core where the magnetic flux is assumed to be constant. This is expressed as equation 3, where L is the inductance of the solenoid, N is the number of turns of the wire in the solenoid, and phi is the total magnetic flux through the solenoid. The total magnetic flux is found from equation 4 using cross-sectional area A, the magnetic permeability mu, and the length of the solenoid. The cross-sectional area A, number of turns N, and the length of coil are all constant. Mu is not a constant and can be represented as a function of temperature. Hence, inductance becomes a function of temperature, which is shown in equation 5. The formula is used to calculate the resistance of the coil as shown in equation 6, where the length of the coil, the parasitic resistance, and the cross-sectional area are used. If a sinusoidal voltage with constant frequency and amplitude is applied to the coil, the current flowing through the coil becomes a function of temperature. The partial differential equation used to relate current to permeability with respect to the temperature is given as equation 7. This equation is used to set the design parameters. The table shows the design parameters that are to be chosen or measured, and these are the number of turns of coil, length of wire, resistance of wire, parasitic capacitance, cross-sectional area, and the voltage applied. The system requirements are shown in Table 2. These requirements are temperature range, accuracy, resolution, frequency of operation, dimensions, response time, electrical connection, environmental rating, mounting options, operating constraint, and target price.